So here we are in lecture 4.2. We're going to continue working on computational Boolean algebra, and we're going to continue our discussion of Boolean satisfiability, or SAT. In the last lecture, we introduced conjunctive normal form CNF as a representation scheme, and now we're going to show how does one actually start with a set of clauses in a CNF style and answer the question as to whether it's satisfiable or not. And it turns out, we shouldn't be surprised, it's another recursive sort of computation, but more importantly, there's a very powerful and important iterative sort of computation that says, more or less, let's just assume that a particular variable has a value, and let's just see what happens. When you have a Boolean equation with many, many variables and many, many, many clauses, it turns out you can get most of the work done with this simple procedure. And this is called Boolean constraint propagation, or BCP. And what we're going to talk about next is how BCP works.
So in the last lecture, we said that Boolean satisfiability had two big parts. It had a decision part where we more or less arbitrarily decide to set some values to variables. And we go simplify the CNF form, and we see what happens. Can we satisfy it, or are we conflicted, or what happens? The problem is that's only going to go so far, and it turns out that because some variables have values, you can deduce that other variables must have values. And it turns out that in a really, really big instance of a CNF, for a really big Boolean function, there's an enormous amount of this deduction that is possible. In fact, this is where really all of the deep work happens in Boolean satisfiability, and this stuff has a name. It's called Boolean constraint propagation. So, given a set of fixed variable assignments, what else can you deduce about the necessary assignments to other variables? Well, you can do that by propagating constraints. Now, there is a very famous strategy for this called the unit clause rule. And gosh, this is like 50 years old. A clause is said to be unit if it has exactly one unassigned literal. Right? And so a unit clause has exactly one way that you can satisfy it, and so what that means is that you have to pick the polarity that makes the clause one. You don't have a choice. You don't get to arbitrarily pick the polarity of that literal, and that choice is called an implication. So here's a little Boolean function, phi, a plus c, b plus c, not a plus not b plus not c. And let us assume that we have decided to make these choices. So a is a 1 and b is a 1. So what do we know? In the first clause, a is a 1, and so that clause is satisfied. I can stop worrying about it. And in the second clause, b is a 1, that clause is satisfied. I can also stop worrying about it. But in the third clause, the a term becomes a 0, the b term becomes a 0, and oh look, what has happened? This clause has become unit. And it's unit because there's exactly one unassigned literal, which in this case is C bar. So what do I know? I know that C must be 0. It has to be a 0 because the only way that I can satisfy this clause is if C is a 0, and then that clause becomes a 1. If I really want to satisfy this Boolean function, because of the decisions I have made for A and B, I have deduced that C by implication must be a 0. It turns out that in gigantic CNFs for real industrial circuits, you get to deduce a zillion of these unit clauses. You get to deduce a zillion variable values. It's really what drives the SAT process forward in any real SAT engine. Let's go take a look at sort of how that might work. So I have got a little example here, and this is an example from this paper, which is worth checking out, by my friends João Marques Silva and Karim Sakala, done when they were both at the University of Michigan. Marques Silva is now at Dublin. So phi, my little Boolean function, has 9 clauses, omega 1, omega 2, 3, 4, 5, 6, 7, 8, 9, 9 clauses. And omega 1 not x1 plus x2, omega 2 not x1 plus x3 plus x9, omega 3 not x2 plus not x3 plus x4, omega 4 not x4 plus x5 plus x10, omega 5 not x4 plus x6 plus x11, omega 6 not x5 plus not x6, omega 7 x1 plus x7 plus not x12, omega 8 x1 plus x8, omega 9 not x7 plus not x8 plus not x13. Gosh, it's not easy to tell if these things are satisfiable, is it? And imagine if it's hard for a function that has 13 variables. Imagine what it's like for a function with 13,000 variables. This is why we need a computational approach to asking and solving these problems. So how do you start? Let's start by just somewhat arbitrarily doing a partial assignment. X 9, 10, 11, and X 12 and 13 are assigned the values shown here. X 9, 10, 11 are 0, X 12 and 1 are 13. We're going to go look at the clauses in the function, and we're going to just simplify them by inserting those values. And so here we go. I've inserted values for 9, 10, 11, 12, and 13. Okay, so what happens? The answer is that not much happens. I cannot satisfy any of these clauses. There are no conflicts in these clauses. There are, basically there's no unit clauses here, which is sort of the interesting part of this exercise. I can't really do anything. So pretty much I can say, now what? And the answer is, I guess I'm going to have to go decide arbitrarily to set some more variable values because nothing interesting happened here. I really haven't, I haven't been able to conclude anything. All right, so what are we going to do next? We're going to choose to assign a variable to a value, and we're just going to choose to assign x1 to be a 1. So I'm going to go back to my Boolean equation here, and I've got all the previous assignments from the last round grayed out, and I'm going to assign these values. And what happens is, in clause omega 1 and omega 2, the x1 term becomes a 0, and in clause omega 7 and omega 8, the x1 term becomes a 1. Oh, this is good, actually. This is helpful because in these first two clauses, and I'm going to circle this here, in these first two clauses, things have become unit. In clause omega 1, x2 stands alone. It's the only variable without a value. I know what it has to be. It's got to be a 1. And in in omega 2, x3 is the only variable without a value. Everything else is a 0. And so I know x3 has got to be a 1. So my unit clause rule tells me, hey, I have figured something out. x2's got to be a 1 and x3's got to be a 1, or I can't make any further progress. And similarly, I've got a couple of clauses, x1 in omega 7 and x1 in omega 8. Hey, those two clauses are satisfied. I can stop worrying about them. That's great, right? So, hey, I feel like I've actually made some progress. Two of my clauses fell off my list of things I have to worry about, omega 7 and omega 8. Two more of my clauses fell off my list because they were unit. I know what happens to them. X2 and x1 are x2 and x3, sorry, are a1. Let's go forward and see what happens. So here we are. I have again grayed out all of the assignments that we got up to this point, and I am about to actually set x2 to 1 and x3 to 1. So let's see what happens. This is what happens. In clause 1 and clause 2, x2 and x3 respectively become 1, and it's satisfied, no surprise. But in clause omega 3, x2 and x3 now take the value 0, and x4 has been exposed as a unit, literal. This clause is unit. I don't have a choice. I now know exactly what has to happen to x4. x4 has to be a 1. This is just an example of this fact that just the fact that I assigned a few values to variables means that a whole lot of other variables must take values if we are to proceed toward a satisfiable solution. And in these gigantic industrial scale SAT problems, the BCP just goes on and on and on and on. It's really the deep algorithmic heart of these techniques. So x4 is a 1. We have discovered that clause omega 3 is unit. That's great. That tells us something. We can go forward and we can simplify. So let's see what happens. So we are about to set x4 to be equal to a 1. And again, I have grayed out all of the previous assignments. And so if I go in and I set x4 to 1, well, clause omega 3 is satisfied. No surprise. Clause omega 4 is now unit because x4 is a 0. x5 is exposed as something that must have a value. And in clause omega 5, x4 is also a 0. Literal x6 is exposed as a value that I now know. So I have now discovered that x5 and x6, we can deduce that they must, by implication, have values. They have to be 1 and 1 respectively. x5 has got to be a 1 and x6 has got to be a 1. Great, I feel like I'm making progress, you know. I continue to uncover clauses that are a unit. I make the assignment that makes that clause satisfied, and I uncover other clauses that are a unit, and it just keeps going. It's like, wow, this thing is simplifying itself. So let's go make that assignment. Omega 4 and omega 5 are now unit clauses. We know what x5 and x6 have to be. Let's go do it. So moving forward, we are about to assign x5 and x6 to both values 1 respectively. And let's see what happens. Well, in clause omega 4, x5 is a 1, omega 4 is satisfied. In clause omega 5, x5 is a 1, it's satisfied. And something bad happened. Uh-oh, look at what happened in clause omega 6. Not x5 is a 0, not x6 is a 0. That's not happy, right? Clause omega 6 has now become unsatisfied, right? Clause omega 6 is a conflict. Because of all of the implications to get to this point of the other clauses that had to have values of certain variables, in order for them to be satisfied, clause omega 6 is necessarily conflicted. Oops, sorry. This is the way this works. This is why this sort of problem is recursive. You go until either something happy happens, like you find an assignment that satisfies it, or you go until something unhappy happens, like, oops, I got a conflict. I guess I'm going to have to undo some decision very early on to make some forward progress. So pretty much, you know, when you run a SAT solver, when BCP in the heart of the SAT engine finishes a pass, there are really three things that can happen. I could have found a SAT assignment of all the clauses I was working on, so I could return a 1. Many of these clauses were satisfied. Or things could be unresolved. We did, in fact, have an unresolved clause. Clause omega 9 here is unresolved. I don't know enough to know if it is or is not going to be satisfied. But, you know, what was really the kind of the biggest problem here was clause omega 6 became unsatisfied. It was a conflict. We found a conflict. One or more of the clauses evaluate to 0. What do you have to do? You have to undo one of your decided variable assignments. You have to go way back up to the beginning of this process where you arbitrarily decided a variable value, and you have to undo that and try something different. This has a really famous name. This is DPLL. So this is Davis, Putnam, Logeman, Loveland. So Davis and Putnam published the basic recursive framework for solving Boolean satisfiability in 1960. Wow, that was a long time ago. And then later, Davis, Logeman, and Loveland found this smarter Boolean constraint propagation, and they proposed the unit clause rule way back in 1962, so slightly over 50 years ago. And amazingly enough, it's 50 years old, but it's still the heart and soul of every modern SAT engine. And it's often called Davis-Putnam, DP, in honor of the first paper, or inaccurately, Davis, Putnam, Logeman, Loveland. The four of them never actually did publish all this stuff together. And the big ideas are a complete systematic search of the variable assignments, a recursive framework for doing that. The CNF form is a useful form for efficiency because you can tell immediately if this thing can't be satisfied because one of the clauses is a 0. And BCP with unit clauses to make the search stop earlier, resolving more assignments without recursing more. And so this is really, really famous stuff. It's so famous it's got its own Wikipedia page. Hey, hey. So that's definitely worth checking out if you want to know a little bit about the history. And in fact, a lot of these folks, despite the fact that they were publishing this stuff in the early 60s, are still alive. They're getting up there, but they're still around. You can even go look at their individual biographies on Wikipedia, which is kind of interesting. Now, SAT has had huge progress over the last 20 years. So DPLL is where this stuff starts. But SAT has been the subject of intense work, and unfortunately, just giving the sort of the rather compressed time constraints of our MOOC, I don't really have the couple of weeks it would take to sort of talk about all the interesting stuff that goes on, but there's really 4 things going on. There are efficient data structures for the clauses so that you can search them fast, right? There are efficient variable selection heuristics so that you can decide to select a variable that has a likelihood of giving you a lot of Boolean constraint propagation action, probably going to create a lot of clauses that go unit and simplify. And that's sort of like, wow, that's a cool idea. How do you do that? Well, there's some really interesting heuristics that let you do that, so you can find lots of implications. And there are some amazing efficient BCP mechanisms. And the reason is that SAT spends almost all of its time inside BCP, because you spend all of your time finding clauses that become unit, finding the variables in them that are unit, assigning them their implied values, and then going back to the clause database and figuring out what you have to assign it to next. And you need a very, very lightweight touch. You need to make sure you don't look at a clause that can't possibly be unit, and that you do the least possible computational work on the clauses that are unit to figure out what to do. There's some really cool data structures that let you do that. And then there's actually some things called learning mechanisms. They're called conflict learning. You can, as you are proceeding down the recursive search, find patterns of variables that can never lead to satisfiability. You can learn them. And what learning them means is you can actually create a new clause in the database that captures the structure of these variables, and you can add it back to the database so that you will never try to find that pattern again, and you can avoid the inefficiency of constantly cycling over these subsets of variables that must avoid certain patterns of their ones and zeros. Very interesting set of algorithms. The result is there are good SAT codes that can do huge problems. What's a huge problem? A huge problem has 50,000 variables. A huge problem has 25 million literals. A huge problem has 50 million clauses. You wonder why I said, hey, why can't I build a BDD for each of the clauses to tell whether it's equal to 0 or equal to 1? This is why. Nobody wants to build 50 million BDDs. All right? That's just not happening. So the result of these very cool efficiency mechanisms over the last 20 years or so has been some amazing SAT codes. You can actually just go out and find these things. There are lots of them. There are many good SAT solvers available online, open source. So Minisat from the two Nicholases in Sweden, very famous, tiny little minimalistic solver code, very easy to grab and go put on your personal machine if you have one. We are going to use this one in our MOOC. We're putting this out in the Coursera servers for you to play with. Chaff from Sherrod Malik and his students at Princeton University, Grasp from Marque Silva and Sakala at the University of Michigan. If you go do a little Googling, you can actually go find all of these things. And this might be interesting for you to do so. Boy, there's just lots and lots of information on SAT out there on the web. I would encourage you to go look around. There's a lot of interesting information you can read, but this is going to be our discussion of sort of what happens on the inside of SAT. What we're going to do next is ask the question, well, we have an engineering view of the universe. We're VLSI people. We're trying to design, big blocks of gates. Now what do we do? How do we take something that looks like a real logic design and apply SAT to it to do something useful for us? So let's go talk about that next.